Okay, well, here we go. What we have taught so far was basic dimensioning and the alphabet of lines, among the other things. But today we're going to expand, and we're going to see how that rule number one applies. So by the way, without exception, all of you that went through defining the rule number one for your textbook, let me just suggest, okay, to expand that a little bit. Because what most of you did, you just copied the book, which is fine. That obviously makes me see, okay, that you have read this. But the rule number one basically dictates the size feature also control the form to the extent of the size tolerance. So if you have something like we have here, that this particular shaft of tin is 1 inch plus minus 5,000, by rule number one, if that pin is produced at 1 inch of 5,000, that will be at its what? Maximum material condition, right? And under rule number one, that means when the physical feature size is at its maximum size, allowed for strain tolerance, therefore its form has to stay within the perfect envelope form. In other words, that pin cannot extend in its straightness beyond the size, which basically means this. Okay, if this pin is produced at 1 inch and 5,000, that pin cannot be like this, expand by any number of thousands. Okay, this pin has to be perfectly straight at 1 inch and 5,000. Well, what happens if that becomes less than 1 inch 5,000? Well, as it departs from the maximum material condition, the form is allowed to depart from its perfect envelope form. So let's just say how that plays. If we have a pin that is produced at 105, even though with geometric dimension and tolerancing in a feature control frame, we have a 3,000. That is the maximum out of straightness allowed. If you were to have that feature control frame underneath of the basic size and dimension, that means you would be able to go up to 3,000 out of straightness. But in this particular case, what happens if we produce a 1 inch of 5,000? I just stated. That tolerance, okay, for that particular one is going to be what? 0. So why is it important for you as a mechanical engineer in your design? Okay, well, simply because every part is going to fit somewhere else, right? You're going to have a main part. So if your tolerance stays under the ASME Y14.5 1994 or 2009 revision, that's a dimensional standard revision, that can better be straight. Okay? Let's suppose that she's a manufacturing engineer. And how expensive is going to be for her to maintain that to be perfectly straight at 1 inch and 5,000? Well, in short, it will be very expensive because we have to have some variance. Well, you as a design engineer have allowed to go plus and minus 5,000, but if she was to produce at 1 inch of 5,000, she does not have any out of straightness tolerance allowed. It's a very critical concept to understand. Okay? So, what would she do in order to basically be competitive price-wise and otherwise? Well, obviously try to what? Keep the size down, below that. Anywhere between the maximum material condition, which is 1 inch of 5,000, to 995. Now, the other thing too that she has to keep in mind is through the process, when the cutter gets dull, the size increases in its feature, which is only natural to understand why, right? Because when the cutter is sharp, it's going to cut close to what is intended in that particular cut. But as it becomes dull, then the size is going to go up. By how much? Not very much, by a few tenths of a thousand, but might very well be over the required limits. So if we understand the concept of rule number one, then what we the appropriate straightness allowed, okay, to this size? Anyone? One at a time, please. Well, let's just see what I just said a minute ago. If the physical feature size is its maximum size, it has to assume the perfect integral form, which means no out of straightness period. But as it departs from the maximum material condition towards the least material condition, it can violate that perfect form to the same extension of the size it departs. Okay? So what would that be? Well, we went from 1 inch and 5,000 to 1 inch and 4,000. So what is allowed here? Right up, 1,000. And here is a concept very clearly defined, and a lot of people misinterpret. Okay? You see what the confusing part is? It says 3,000, up to 3,000. And the emphasis or the key point here is up to 3,000. It's not 3,000 period. Okay? Up to 3,000. And so what happens in industry, still today, believe it or not, after all these years, when it comes to this, people say, okay, 1,000, it's out of straightness when we check, that's good enough. But then, when it comes to 1 inch and 3,000, how far we have departed from 1 inch and 5,000? 2,000, right? So we have, that's allowed 2,000. A 1 inch and 2,000, we're going to have 3,000. And 1 inch and 1,000, how much are we allowed to go? What is it? That is 3,000 all the way down. You see, the feature control frame tolerance limits us to absolute 3,000. No more than that. But we have to make sure that we understand how this 3,000 applies. Again, at the maximum material condition, it's a 0. As we depart from the maximum material condition, it is for each 1,000 of departure from the maximum material condition, we gain a 1,000 out of perfect form. Does this make sense? Yay, it does. Okay. How critical this concept is for you as an engineer, design engineer in particular? Absolutely the most critical concept to really understand. Because you're going to see in a few minutes, and certainly you're going to find out once you're on the job, okay, how that interplays in the context of everything else when it comes to assembly. Okay, so once again, the RFS stands for regardless the feature size. Okay? Why do we say that? Well, this is called a feature control frame. Okay, this is feature control frame, for short FCF. In the absence of any modifier in the feature control frame, and you know what modifiers are, right? How many modifiers we have? Well, we have 2 modifiers. One is the maximum material condition, and the other is the least material condition. And one stands for MMC, or circle M in the feature control frame, and the other stands for LMC, or circle L. So if we don't have a modifier in a frame such as we have it here, then obviously that means that's regardless of the feature size. Well, let's see how this applies to this here. It still is regardless of the feature size. However, we do have something there. And that symbol indicates it's the metrical tolerance zone. It is not the surface control, it is the axis control. So it's a big distinction between surface control, if I were to have this part and check my surface to find out how much out of straightness it could be, or this is the axis control, meaning the central axis of that part. Okay, well, let's see how that works. What would be the tolerance at 1 inch and 5,000? Remember, it says regardless of feature size. Okay? Therefore, by that definition, it's going to be 3,000. So that means the rule number 1 does not apply to other than surface control. Since we have just evoked its axis control of the feature, then we have 3,000. And 3,000 is going to be all the way from the maximum material condition to the least material condition. Okay? For your sake, I would suggest you kind of jot it down in your paper or whatever technology you use, because today's going to be quiz, the next time is going to be test. And so it's a very important concept again to deal with, right? And of course, if I'm clear, if you don't quite understand what I'm talking about, raise a question. Yes?
Max material was just talking about, as far as like...
It's in English, by the way.
Yeah.
But remember what kind of English? That is international language.
It's really going back to what you were saying before, like from the 5,000s, or from the actual size, and then you have to go from 0. Why does it end at 3,000 again? Is it because of that? What does RFX stand for?
Okay, we all agree that nobody can produce a basic size. You cannot produce 1 inch, okay, because it's always going to be somewhere over or under. Okay, we understand that, right? Therefore, we all agree we have to have a variance. And you as engineer is going to assign a variance. How much on the positive side, how much on the negative side, which is called plus or minus, okay? Well, in this particular case, in your calculation of the mating, okay, components, you found out that you can live with size up to 5,000, under 5,000, okay? So you have a maximum material condition by defining what the rule number 1 states. You have from 1 inch and 5,000 to 995. And when I check that size, as long as it conforms to that range, that part is as good as gold, as far as the size control goes. Okay? We understand that. However, we understood from the past lectures that besides the size control, we also have a form control. That while this top of this desk is flat, seemingly flat, but we know it's not perfectly flat, right? I mean, it's got peaks and valleys, maybe in terms of tens of thousands or just thousands, but nevertheless, it's not flat. We know that this is round or it's cylindrical, but it's not perfectly round or cylindrical. Therefore, that's called a form control. So the rule number 1 states, again, when the part is produced at the maximum material condition, meaning for outside dimension, that's outside the dimension, like 1 inch 5,000, then it has to assume the perfect envelope form. What does it mean? In order to check this here, you see this pin, as it produced, depending on the length and whatnot, it could be crooked. It could be out of straightness. But how do we check that out of straightness? Well, we would define the gauge. We're going to have a gauge. And that gauge is going to be simulating our maximum material condition of that feature, which means that this gauge is going to be 1 inch and 5,000. Okay, so imagine now you have a bushing. Okay, the same length as the pin is, and that bushing is produced at 1 inch and 5,000. And so when I take that pin and I try to slide through the bushing, if it meets that, even though it's bent, but if it goes to the bushing, that means it met the size requirements, and obviously must be meeting what? The form requirements. That's what it's called the perfect envelope form, because it is like an envelope. We all know what the definition of envelope is. Okay, so that's very easy to check the form control of any feature, particularly of that relatively small size. Okay? Does this clear up somewhat?
Somewhat, yeah.
Now, as it departs from that maximum, that's why it's 0 there. As it departs from the maximum material condition, as much as it departs from the maximum material condition, that much out of straightness is allowed. That's why we see that 1 inch and 4,000, we depart only 1,000, right? So it could be out of straightness by 1,000. As we go 2,000 below the maximum material condition size, well, that will be up to 2,000. When it comes to 1 inch and 3,000, we're going to be basically at 2,000, and 1 inch and 2,000, 3,000. But below that, we cannot exceed this here. Okay, this 3,000 absolute governing factor that says up to 3,000. So if you happen to be quality control, if you happen to be a quality control engineer, and the parts are shipped by 18-wheeler, it comes to your shop, and you pick few to check. You check the size, okay, that meets the size range. You check the form, and based on that scale there, that's what you're going to have to keep in mind. You don't have to write it down, but just based on that, if you check something and you find that that a part is 1 inch and 1 inch, okay, but it is, okay, more than 3,000 hours straightness, you would reject the whole 18-wheeler to go back to its origin. Okay, all right. Now, as I said, the equally important part is to understand, even though we have the same condition, okay, but this symbol here negates the rule number 1, which simply means we are not controlling the surface any longer. We're controlling the axis. But what does it mean? If I take this part and I turn 360 degrees or 180 degrees, right? What happens? My top becomes bottom, or my bottom becomes top. And so if the pin is bent, it's going to show, of course, if I have a dial indicator, right? It's going to lump, it goes up and down, it's going to show that variation. But we are controlling the axis. Basically what we have here, we have a pin that is basically is going to be, let's suppose that that's going to go 3,000, and that means that is a 3,000, okay, allowed, from the larger size to the medium size, okay? So if you had a test and I said, okay, does rule number 1 applies for other than form, control? The answer is no. Simple as that. The answer is no. Okay. Now, to add a little more kind of a juice to be fun, okay, what we have here, we have now a modifier. Okay, we have a modifier that simply states it is a maximum material condition. At the maximum material condition, we are going to find is going to be 3,000, because that's what it stated, at its maximum material condition, right? As it departs from the maximum condition and becomes 3.4, it's going to be 4,000. Whoops. What does it mean? It allows us to have a bonus tolerance. For every 1,000 departed from the maximum material size, under the maximum material condition, okay, in the feature control frame, we gain that much out of straightness. So we have a stated tolerance, which is 3,000, plus 1,000, okay, which is below the maximum size. Therefore, we have to have 4,000. It will be allowed up to 4,000. Okay, anyone, what would be the out of straightness, okay, allowed at 3,000? A 1 inch and 3,000. Anyone?
5,000.
One at a time. Well, obviously, if it's stated at 3, how much we deviated from 1 inch and 5?
2,000.
Okay, so if this right, 3 we deviated from 5, so it's going to be 5,000. Okay? If we are going to go to all the way down to 995, how much would that be? Well, we deviated, okay, from 2,000 to 1 inch and 5 to 995 is 10,000, right? So we have 10 plus 3, then obviously this is going to be 13,000. See? Now, for her as a manufacturing engineer, since we designated her to be manufacturing engineer whether she likes it or not, Okay, that means that would be the least expensive way to go and produce these parts. Because she not only has the modifier here, but the modifier allows her to deal with the bonus tolerances. Okay? So that's very critical. Okay, now, that is the maximum fill condition. What happens if I were to have another feature, I forgot to do this, but I will do it here. It's still straightness, okay, under 3,000, under least material condition. Okay, let's stop and think about it. It is completely reversed, okay, option that we have now. It says 3,000 at the least material condition. Okay, so what would that be at 1 inch and 5,000?
8,000s, 1 inch 8,000s.
Based on what?
The least material.
What is the least material condition in that particular pit? The smallest possible size.
The smallest hole we would have.
That'd be 995, right? That's from 1 inch to 5 to 995. That's the least material condition. So it's 995. How much is from 995 to 105? Well, it's 10,000, right? So we have, again, it's reversed, okay? So we have, okay, from this here, this is going to be here 13,000, and this here is going to be 3,000. So that, it's opposite, it's a reverse, okay, scenario that we have. Do we get that? Everyone? Not quite, sort of, who cares? What's critical here to understand, folks, is what kind of modifier we have. First of all, are we controlling the form? By rule number 1, form control means, okay, if the feature of size that is perfect, if it's a maximum material condition size that's outside or inside dimension, okay, it has to assume the perfect inverse form. Therefore, even though I do have a feature control frame there, as you see, okay, 3,000, it still means, okay, that has to be perfect form. There's no allowed deviation on the straightness, right? As it departs from that, then equal to that departure, it could be out of straightness, it could be out of perfect form, okay? In this case, what we have a modifier, which is maximum material condition modifier. That means under that condition, the tolerance is going to enlarge as it departs from the maximum size allowed per print tolerance. By the same token here, we have a least material condition, which is another modifier. And that also means the same thing, except in a different direction. When the part is produced at its smallest possible size, is going to increase from that smallest size to the largest possible size. I really cannot impress you or intimidate you with this principle, how critical it is for you as a future engineer to really understand and to use in your calculation. Because you're going to see in a minute when we talk about how to calculate the mating part size, as we discussed so far, and you know that these parts have to mate somewhere. Otherwise, they're going to be paperwork, right? And so for that mating part, by the way, the same principle we had here. Now, assume that we have a shaft that is 24 inches long and is relatively small in diameter in relation to its length. Therefore, if it's 3 or 4 times the diameter of the feature, if it's 3 or 4 times the length of that feature than its diameter, then what you're going to find, okay, there's going to be some problem with supporting that part if it's going to be turned on the leg. And therefore, most likely the deformation is going to take place. So in order to control that, we have a so-called per unit control. We are saying the overall auto straightness could be allowed up to 20,000, but per unit length, or 1 inch, only 2,000. But what does it mean? That means this. If I have a shaft, it's going to be, let's suppose this is 24 inches. Okay? And that shaft can basically, in a Zander form, be like this. That simply means this. The total shaft cannot exceed 20,000 hours straightness. The total shaft. But you remember, if you never worked on a typewriter, but there was that carriage return. You kick that carriage return, and it just flies back. Okay. Well, usually that carriage return is only like a bushing, if you will, threaded bushing, 1 inch long, the longest. Okay. So to control the overall length, we're going to design a gauge that's going to be at its what? So-called the virtual condition, which will be what? If I use that pin, okay, they're 1 inch, and it's going to be 24 inches long, because I indicated here, what would be that bushing size to simulate the functional gauge? Meaning that bushing size, provided it's perfectly cylindrical, but to simulate, in other words, I would take that shaft and just throw it through the bushing in order to go through that. Well, obviously it's going to be what? 1 inch, and it's going to be in 20,000, or 1 inch and 25,000 according to this here. Because the pin can be produced up to 5,000 over 1 inch, and 20,000 on a straight, that will be 1 inch and 25,000. So if I make the bushing 1 inch and 25,000, that would be functional gauge for the same length. All I do is just drop it down and goes through that, and that's basically given, okay? But if I have that unit control, 1 inch, okay, right there, that means that I'm going to have another gauge, which is going to be only 1 inch wide, or rather long. And I can imagine now that pin or shaft is up to 20,000 bent from end to end. But bushing is going to be only 1 inch long, and I will be able to, by that analogy, I will be able to check my entire length on each basis, on each unit basis, right? So as you can see in manufacturing, where we really have a very easy way to verify something, not as easy to produce because there are certain techniques that you have to apply. Most definitely you have to consider as a design engineers, how you're going to fit all of this together based on the size, based on the dimension, okay, the lengthwise and otherwise. And so that's why I find that in this particular lab, the most critical part which you can hopefully help yourself is clarifying these basic principles, which most likely has not been covered in your previous classes, nor, I would suspect, will be covered for the balance of your program. So please, don't be bashful. Hey, if something is not quite clear, then just raise your hand. I can try to go back and redirect, but basically still going to end up with the same thing. Okay? Any questions? But there's so many questions, you know where to start from, right? How much of time have you had in general dimensioning and colors? Not much. Well, very likely you're going to have a bunch of time, okay, when you get to work, except you're going to have to squeeze that among all other things that you're going to be faced with. So, it'll be much easier and cheaper, if you will, okay, to clarify right here while you are in this class. I'm not talking about today, that would be wonderful if you could. But there's a lot of, I realize, there's a lot of information. Truly, it's not that much if you really get to the bottom of it. But this is a different language. And as I indicated, this is not a Serbian or Russian or German. It's as English as apple pie, as I understand it, usually the saying around here is. It is truly the most fundamental principles of it that you have to deal with. And that's going to basically reflect on your promotions and everything else that you're going to be faced with. Okay, how do we stand time-wise? Okay, before we take a little break off, I think at least I need it enough to recognize that without the feature control frame tolerance, this is basically a legitimate call-out, as we would call it. It has the basic size, it has a respective variance stated there, but without the invocation of the given standard, that means that particular part could be 1 inch at 5,000. It could be bent as much as it turned out to be. And that certainly is going to produce, to give you some problems. Now, why is it important we recognize the GD&T? Because we have, and there's another factor there that we have to consider, and that's the virtual condition. A virtual condition for outside dimension is going to be when the size is at its maximum material condition plus geometric tolerance. That virtual condition, that formula, I'm going to hold you responsible for that. When its size is its maximum material condition plus the stated geometric tolerance. Well, okay, let's say in this case, what would be the absolute minimum size of a mating part? For 1 inch and 5,000, so let's have it score. It's going to be 1 inch and 5,000 plus what is the geometric tolerance? 3,000. Okay? So it's going to be 3,000. Therefore, it's going to be 1 inch and 8,000. That will be absolutely the minimum size of the mating part. In this case, it would be like a bushing. Okay? That's called virtual condition. Combined condition of its size, its form, and its tolerance. Okay? That's for outside dimension. For inside dimension, if you want to calculate, which is certainly going to come out with this, is going to be virtual condition for ID. Is going to be again size at maximum material condition minus geometric tolerance. Okay, why that? Well, because in this particular case, if I have a bushing, that's going to be called, let's say, one inch plus minus 5,000, okay? And it's going to be straight, okay, within 3,000, using the same analogy. That means that I would allow that bushing in the maximum material condition. What's the maximum material condition of this bushing? Well, it's going to be the size, it's going to be size of the maximum material condition minus geometric tolerance, and that would be 995 minus 3 is going to be 992. That means the pin, if that bushing turns out to be bent, like this, okay, that means that my pin is going to have to be that size. See how beautifully it kind of fits in one into another? And with the virtual condition effect, you and I will never have problem in our assembly. What generally happens, okay, you got a bunch of refrigerators there, or dishwashers, or the cars on the production line, and then the guy grabs a pot and wants to finish something, it just doesn't go. Whoa, well, what happens then? Well, it's a headache for everyone. Because usually it goes with the panic button on your production line, hold up. Then go try to find some part that is going to fit that part, okay, and so forth. But if we use virtual condition calculation, there's no problem whatsoever. That's how critical it is. I cannot overstress how critical that concept of the basic geometric dimension and tolerancing is to understand. Now I know that you're all going to be doing fancy work with Pro Engineering, AutoCAD, you name it, you know, whatever the beautiful drawings are there, okay, and so forth. But it doesn't do any good or to her if it hits the floor, okay, and we have to produce something. The beauty is, well, what is the old saying around here? For the eye of the beholder. But the actual engineering drawing is for somebody to actually produce something. Okay. Anything to add? Anything to subtract? Or okay, well, I'll tell you what. You're going to find your chapter 4 in your textbook. Okay, so I assume everyone's got a textbook. Make sure you go through that. Reread again. Building modifiers, maximum material condition, least material condition. In chapter 4 and 5, okay, for your reading pleasure, if I could use that word, okay, you're going to find even some clarification of the very concept I'm trying to expand today. And if you do have a question, obviously bring it with you. You're also welcome to drop me an email. Drop me an email, and I'll be more than happy to see if I can answer, okay, that way. I do have a Skype, but in the past it didn't prove out to be very practical. Because I had people be calling me on Skype, okay, when they were in the midst of the party and probably one too many beers. And they want to talk about geometric dimension tolerance. And that's not a very good combination. Okay? Any questions? Any comments? Now, going once, going twice, it's like, well, going 3 times, gone. Okay, we are going to go ahead and make some chips today, as we did 5. We had a very good session, by the way. And so, 2, 4, 6, 8, 9, that's beautiful numbers, so we all can work on that. You all have your safety glasses, right? Okay, once again, keep in mind, I have only 3 or 4 safety glasses around the goggles there, which I personally would not use, but I cannot tell you not to, or to force you to. But you cannot operate any machine tools in lab without safety glasses. And now, let it be the last day, okay, the last kind of friendly warning. The next time, if you show up without your own safety glasses, or keep in mind, only 3 or 4 we have, there are 9 of you here. So I'm going to just have to excuse those of you that don't have safety glasses. You will not be able to be behind the machine. By OSHA standard, you really have to wear glasses as soon as you walk in the lab. I'm not that critical, but I cannot put you on the machine behind the machines. Okay, you've seen chips fly. All kinds of things happen. Okay. All right, let's take 5-6 minutes break. At least I could use one. And then you don't want to leave everything here. You may see if we have they're down on the floor in my office, okay, next to the desk. These goggles safety glasses right now, so you may want to pick them up. And in 5 minutes, that'll be basically, okay, well, let's say, yeah, 2:45, okay, 3, I'll meet you in the other lab, okay? Thank you. And I'll leave you some board in the case that you do have a last minute question, or you go over that. Mitchell Randall is here, right? Mitchell? No. Okay, let's see. 2, 4, 6, 8, 9. Oh, I have only 8 here. I got White, Preston, Naylor, Knox, Ingram, Gray, Mitchell, Jones, Hassan, Dozier, and Letman. Okay, 2, 4, 6, 8, 9. I think I need new glasses. Okay, folks, let's take a little break and then we go further. And after that, I'll tell you when we come back. We'll take a quiz.